Ladies and gentlemen, this is Saksala from Finland, Tampere University. I work there as a docent and academic research fellow. My topic today is numerical modeling of dynamic punch-through problem. First, I would like to give some background and motivation for this study. So, tensile fractures are frequently observed in the geomechanical applications like geological disposal of radioactive waste, efficient underground storage, geothermal energy extraction, and underground constructions. However, shearing is the most common failure mode in rocks under the compressive stress states in these geomechanical applications, and the failure of rock bridges between two adjacent discontinuities in rock masses mostly develops as shear fracture. For these reasons, a numerical model aiming at realistic description of rock failure processes should be able to describe both tensile and shear fracture types. So this work presents such a model based on viscoplasticity model for shear failure description and an embedded discontinuity finite element model for tensile fracture. And the dynamic punch-through problem is solved as a numerical validation problem. Okay, now we go to the theory of the model. So first, we look at the embedded discontinuity model for tensile fracture. Here we have an element 4-node tetrahedron in 3D. It's cut into two parts by a crack, which is a displacement discontinuity defined by the normal and the tangent vectors. And for that, we can present the displacement and strain field like this. First, the displacement consists of the regular finite element interpolation of the nodal displacement, and then there's a special function m defined as like this as a difference between the Heaviside function and a special ramp function which I explain later. And then there is the crack opening vector alpha d. And then we take the gradient of the displacement, we get the strain, and there are the Dirac delta comes from the gradient of the Heaviside function. Okay. And the function phi is chosen from among the nodal interpolation functions by this criterion. And the task of this function m with this special ramp function phi is to restrict the effect of the displacement sum inside this particular element. And that facilitates the treatment of the essential boundary conditions in the finite element formulation. You can find the details in the relevant literature. We continue here to the finite element discretized problem, and we have these two equations to be fulfilled at each element. First, we have here a balance of linear momentum equation, and this phi is the loading function defining the elastic stress states for the elements with crack. So it depends on the traction vector over the crack plane, which is defined by the Cauchy presentation, the stress tensor, and the crack normal. Okay. So up until now, we have dealt with the tensile fracture, or actually how it is modeled. It is modeled as an embedded discontinuity plane. But how do we solve for the crack opening vector alpha d that was there and the traction? So now we deal with those topics. And how do we deal with the shear failure models? Okay, first, the discontinuity crack with a normal parallel to the first principal direction is embedded when the Rankine criterion is violated. Then the tensile crack opening vector is solved by this model. So you have here the loading function defined as a function of the traction and internal variable kappa and its rate. The first term here is the normal term of the traction, and the second one is the shear term. And the beta here is the shear retention, shear control parameter, so you can adjust its contribution to the loading function. Then we have tensile strength and softening function Q defined here as the sum of the softening term and the rate dependent term. which is defined by the viscosity kind of modulus here, St, and the rate of the internal variable. And then there's the softening modulus, which is exponential one and calibrated by the mode-one fracture energy. Then we have evolution law for the traction vector, and then evolution law for the crack opening jump, or crack opening vector, which is the displacement jump, and it's defined analogously to computational plasticity. It's a gradient of the volume function multiplied by crack opening increment here. And then the internal variable is also defined like this, so it actually fulfills the dissipation inequality of thermodynamics by this choice. And then we have a Kuhn-Tucker kind of consistency conditions to be fulfilled. And here, Tucker-Prager yield criterion with linear softening of viscosity model is chosen for rock failure description and compression, or shear. So it means that the tensile fracture is governed by the displacement plane, and it's this local plane here inside the element, but then the shear fracture is modeled like a bulk behavior. The material outside the crack deforms plastically and account for the shear failure. Okay, we have a Drucker-Prager criterion here, and then the plastic potential. So this is non-associated plasticity. We have a cohesion, and then softening function, rate-dependent softening function again, similar in form to that of intention. So we have a softening modulus. This is a linear softening modulus calibrated by mode 2 shear fracture energy, and then the linear viscosity term. And then we had the evolution equation for the stress tensor and the viscoplastic strain evolution equation defined by the plastic potentials and associated plasticity and internal variable evolution model. And again, Kuhn-Tucker kind of conditions to be fulfilled. Okay, then we look at how do we actually solve for this. We have two models now, the embedded discontinuity model and the shear model. The viscoplasticity shear model. How do we actually solve the whole problem? So the flow of the solution process is defined here in this flow chart. So if we start from here, we perform a loop over all the elements with the strains from the global problem. We calculate the trial stresses and traction for each element like this. And then we check, does the element have a crack? If it has, we go to check the loading functions. And if either of the loading functions is violated, we perform the stress return mapping to obtain a new stress and the other variables. And then we go to the assembly of the internal force vector, and then we go to solve the global equations. And again, increase the time and go further. Start again. But then, if these are not violated, these loading functions, if the element have a crack and there are no violations, so the stress is elastic, the stress state is elastic, we calculate the internal force vector and go to the global solution again. Okay, if the element does have a crack, okay, that was that. If the element doesn't have a crack, then we go to check the first principal stress. If it is greater than the tensile strength, we embed a new discontinuity with normal parallel in the first principal direction. And again, test the criteria. Okay, if this is not fulfilled, and if the Drucker-Prager is not violated, again the stress state is elastic, and then we assemble the internal force vector and go to the global solution again. And the final option here is that if the element doesn't have a crack, but Drucker-Prager is violated, we perform the stress. So the element fails in shear, we perform the stress integration and again calculate the internal force vector and calculate the response further. The details of the stress return mapping can be found in this reference here. Okay, now we go to the numerical example. This is the dynamic punch-through test on marble, and this is the original reference for that. The experiments were done, were published in Engineering and Fracture Mechanics. Now here we have a computational model that exploits the symmetry. It has 156,000 linear tetrahedrons here, and you see here the cracks, the pre-cracks here, all the notches, and this whole setup is carried out in split Hopkinson pressure bar. So we have a transmitted bar models in two node bar elements, and the incident bar external force here comes in as an rate-dependent force pulse. And then we have contact interfaces, a model with imposing the contact constraints, and then we have the reaction forces P1, P2, and the loading is like this, that the P, the loading in comes from here, and it is supported by here at the outer rim of this geometry. So here the shear fracture is expected here. Okay, and here you can see the relevant material properties. The material is some Fangshan marble from China. So before presenting the simulation results, we look at the experimental failure modes. This is the schematic presentation. This is the actual failure mode. So you can see that this block is removed by shear fracture during the test, and then the compressive wave comes in and it removes this. There is some orientation on the crack plane, and here you can see the crack types. There are main shear cracks. They propagate from of these notch bottoms and reach the outer ones. So there is a slight alignment of the crack plane. And then there are secondary cracks, these wing cracks. They were called in the paper, they were called donut cracks, but it's called them wing cracks here. These are tensile of nature, and this is the shear crack, this main crack. And then there are a lot of radial cracks outside there, like this. So this outer piece of the specimen also fails with these radial cracks. Okay, then the simulation results. First, you can see this is the contact force versus displacement recorded. That's something like 45, 50 kilonewtons. And here you can see the tensile crack opening magnitude. So you can see that there are some stronger opening at the corners where the wing cracks propagate. So this model can, kind of an engineering sense, capture this wing crack failure mode. And then you need the viscoplasticity part, the Drucker-Parker part, to capture the actual shear fracture. So you can see here the plastic strain, equivalent plastic strain patterns, and this represents the shear fracture. So it is expected that this middle part is removed as in the experiments. So that much you can predict or say about on the basis based on this simulation. And you can actually also see some radial cracks here. So it actually can be concluded that the presented combined with Drucker-Parker viscoplasticity, and that the discontinuity model captures the failure mode or the salient features of the failure mode in a satisfactory engineering sense in this dynamic transfer problem. The main shear crack is predicted, as mentioned, as the viscoplastic localized strain, while the wing cracks propagating from the pre-crack bottom corners are captured by the embedded discontinuity model. Therefore, its final conclusion is that the model could serve in geomechanical applications involving tensile and shear failures under dynamic loadings. Okay, thank you for your attention.